Hello, statisticians. Mr. Youngstover here from Skew the Script. Today we're going to start our unit on something that underlies everything we do in statistics. That's probability. And we're going to use probability today to analyze the curse of the home run derby. Let's skew it. Today's lesson is on defining probability. This is lesson 5.1 in our course sequence. Let me start by introducing you to Aaron Judge. He's a big power hitter in Major League Baseball, and he's known as such, one, because he has a pretty big stature, as you can see here, compared to Jose Altuve, who's another baseball player. But also, he has a big swing, and specifically, he hits a lot of home runs. Those are hits, they hit so far, they go over the outfield fence, and you score a run. And he participated in the 2017 Home Run Derby, which is an event where players gather to try and hit as many home runs as they can in a certain amount of time. He won the event, and he won it in style. Specifically, he hit a ball so high that he hit the ceiling of the stadium. Take a look.
Yeah, that's what you want to be.
Oh, that's a homer. Gotta give it to him. That's a homer. Come on, it's a home run.
They gotta count the roof.
Safe.
That's not.
They counted it.
Okay.
That's 16. There's 17.
Oh, okay, yeah, you'd be all right.
I love the umpire saying no, like no one.
Oh, another one straight
Went up
away.
and got that one.
In 2022, he set the record for the most home runs in a season post-steroid era. And that year, he was invited back to participate in the Home Run Derby. But shockingly, Aaron Judge said no. He declined competing in the Home Run Derby. And he said it was to avoid the Home Run Derby curse. So what is the Home Run Derby curse? And statistically speaking, is it real? That's what we're going to look at today. If you'd like to follow along using our guided notes, you can print them up at this URL. So first, let's define probability using a simple definition. So we can say probability is the number of outcomes in an event divided by the total number of possible outcomes. This is the simple definition, and you can only use it when all outcomes are equally likely in a chance scenario. So say that there are 8 red marbles in a jar and 12 blue marbles. What is the probability if you shake them up and randomly select one of selecting a red marble from that jar? We're going to say R is the event of selecting a red marble from the jar, and PR is the probability of event R occurring, the probability of getting a red marble. This is standard probability notation. So if we're going to use our formula, PR is the number of outcomes in that event R out of the total number of possible outcomes. What that means practically is this. When you reach your hand in the jar, there are 8 red marbles. So there are 8 ways to select a red marble out of a total of 20 marbles in the jar that you co-selected. 8 red, 12 blue. So we have 8 out of 20 possible outcomes. So 8 out of 20, that's 0.4 or 40% chance of getting a red marble. Now, from this definition of probability, there are some properties that follow it. So one property of probability is that they're always between 0 and 1. 0 meaning 0% chance of happening. There is no chance that it happens. 1 means 100% you are certain it's going to happen. We can see here that P of R, probably a red marble, is 0.4. That is between 0 and 1, so we're good to go there. The probabilities of all possible events should add up to 1 in a chance process, or 100%. Let's take a look at what that means. So for this jar, there were red marbles and blue marbles. There were no any other kind of marbles. So the 2 possible events is you get a red one or a blue one. The probabilities of those events should add up to 1. So the probability of getting a blue marble, there were 12 blue ones out of the total of 20 marbles. You do 12 out of 20, you get 0.6 or 60%. And if you add that to the 40% chance of getting a red marble, you get 1. So this checks out. You've covered all possible outcomes in this chance process, red or blue. When you add those together, you get 1. This means that you covered every single type of event that could have happened in this chance process. And then finally, the complement rule. The probability of event A not happening, i.e. A complement, is equal to 1 minus probability of event A happening. So let's take a look at what that means. So we're going to say PRC, the probability of R complement, i.e. the probability of not getting a red marble, is equal to 1 minus the probability of getting a red marble. So if you don't get a red marble, that means that you reached in and you had to have drawn a blue marble. So the probability of blue marble should be equal to 1 minus probability of red marble. We can check that out. So 1 minus probability red is 1 minus 0.4. When you subtract those, you get 0.6. And yes, that is equivalent to what we found before, the probability of getting a blue marble. The complement rule should make some sense. If something's not happening, it's just simply the 100% chance of all the events minus the chance of it happening gets you the complement. All right, so probability models. This is just a way of organizing a set of outcomes and their probabilities when you have a more complicated chance process. So 2 properties you have to check to make sure probability model is valid are these 2 properties we found before. All probabilities are between 0 and 1, and they should all add up to 1. So say you have a bag of 20 beads, and they're a mix of clear/solid beads and red/green beads. There are 6 clear beads and 8 red solid beads in the bag. There are 2 clear green and 4 green solid. This is the mix you have. The probability model for this situation will look like this. 20 total beads in the bag, and we can get the probability of getting 1 of each kind of category. So for example, for clear red, if you draw in the bag, there are 6 possible outcomes, 6 clear red beads out of 20, that's 0.3. And the rest of the probabilities for the other outcomes are shown here. So to check this probability model is valid, we have to see that all probabilities between 0 and 1. Go ahead and check that. Yes, they're all between 0 and 1, so we're good to go there. And then all the probabilities should add to 1. If we've covered every single possible event that could happen when you reach in and draw a bead, the probability should add to 1. So if we add up all these probabilities, we get to 1. So yes, we've covered all possible events that could happen when you draw your hand into this bag of beads. So we can use probability models to find different, more complex probabilities. So let's say that R is the event of selecting a red bead, kind of like before, and Q is a more specific event, selecting a red solid bead specifically. Find the probability of Q. Find the probability of getting a red solid bead. Well, that's just given to us by our table here. It's 8 out of 20, 8 red solid beads out of 20, 0.4. So we're good to go there. Find the probability of getting a red bead. Well, red means it could be clear red or it could be solid red. So it could be either or of these. And so we can just add up their probabilities, get the total amount of red probability, which is 0.7. Now, probability of QC, that's the complement of Q, i.e. the probability of not getting a red solid bead. So we cover up red solid. This is the probability of getting anything else besides red solid. So we can add up the rest of the probabilities besides red solid, we get 0.6. Now, we could have also used the complement rule. Remember, 0.4 was the probability of getting a red solid bead. So by the complement rule, we can just do 1 minus get that to get the probability of not getting a red solid bead. When you do 1 minus that, you also get 0.6. So the complement rule is valid here. It gets you the same answer. For the probability of not getting a red bead, we can cover up the red beads, and we just have the probability of getting the green beads. That's the only things we could get. So we could do 0.1 plus 0.2 is 0.3. That's the green bead together. But then you can also do 1 minus the probability of getting a red bead. 1 minus 0.7 also gets you that 0.3. So there you go, complement rule. Now we're going to move on to the law of large numbers. So the law of large numbers states that after many trials, the relative frequency of outcomes will approach their theoretical probability. And to test this law of large numbers, we're going to use this applet, which is linked in the description. Go ahead and try it out. So this simulation takes us through tossing a coin. This is a fair coin, 50% chance of heads, 50% chance of tails. And when we toss it, we're going to count the number of times we've had a heads and see, will actually 50% exactly of those tosses be a heads? So let me do one toss. That one happened to be a tails. So there are no heads yet. We don't see any on data set here. But the next one happened to be a heads. So now exactly 50% of our tosses are heads. We can see that our relative frequency of heads has approached that magic 50% number that is the theoretical probability for this process. And 2 is not really a high enough sample size to keep on doing it. We happen to get our tails, okay. Happen to get heads again, okay. And let's keep on going. And eventually, you can see there's going to be some variation, but the law of large numbers states that the relative frequency, the proportion of these tosses that should be heads, will approach 50% in the long run. So to speed that up, I'm going to go toss, 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 toss. We see we're varying a little bit lower than expected number of heads, but we should approach it. We should approach this green line, the magic green line, 50% heads. So I'm going to speed this up. I'm going to do 25 tosses per click here. Toss, 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 toss. And we're getting there, getting there, getting there. I'm going to speed it up even more, 200 tosses per click. And you can see here, as that's going, we are approaching, and getting there, getting there, getting there. We will eventually approach that 50% mark and be very, very close to exactly 50%, as you can see here. So this is what the law of large numbers states. The more times you repeat a chance process, the more trials you will begin to approach the relative frequency predicted by a theoretical probability. Now, this applet brings up one myth that I want to tackle together. This is the myth of being due for one. Say that you have a fair coin and you flip it 10 times. In which situation is getting a tails on the next flip more likely? Here's situation 1, heads, tails, tails, heads, heads, etc. And situation 2, heads, tails, tails, and then a bunch of heads in a row. So in which situation is the 11th flip going to be more likely tails? Well, a lot of people will say situation 2, you've got a bunch of heads in a row, you're due for a tails on your next one. That is completely false. The tails is equally likely in both situations. The prior events have no bearing on the probability for the next flip because the events are independent. Probably doesn't change because of previous results if you have independent coin flips. And now we're going to move on to our discussion for today. So we talked about the home run derby before. It's competition to hit home runs in a certain amount of time. The best hitters in Major League are invited to compete. It happens midway through the season. They play the first half, find the best hitters, invite them to the home run derby midway through, then they play the second half of their season. And unfortunately, there's a phenomenon commonly known as the home run derby curse. Ooh. So to see what the curse is, you first have to learn about this statistic called the batting average. So your batting average is your proportion of at-bats that end in hits, which is a good thing, rather than outs, a bad thing. And your batting average is equal to the number of hits divided by your total at-bats. So say that you go up to the plate 100 times, you have 100 at-bats, and you get 30 hits. 30 out of 100, that's 0.3. This means that 30% of the time you got a hit. And this is considered a very good batting average. Hitting is hard, so getting a hit 30% of the time is actually a very good thing. So here's some prior players in prior year home run derbies. We'll start with Bobby Abreu. So in the first half of his season, in 2005, he had a .307 batting average. It's a very good batting average. This means that 30.7% of his at-bats ended in hits. It's very good. Then, because he did so well, he got invited to compete in the home run derby. He actually ended up winning the home run derby. But then, unfortunately, in the second half of the season, .26 batting average. He fell off. So he was worst hitter in the second half of the season. Let's talk about Aaron Judge. So Aaron Judge in 2017 had a batting average of .329. That's a very, very good batting average. And as we saw earlier, he won the 2017 home run derby, but then he really fell off. .228 batting average in the second half of the season. So you can see why in 2022, Aaron Judge declined to do the home run derby because he saw his performance drop off. Maybe that was informing his decision. Talk about Juan Soto, who ended up winning the 2022 home run derby, maybe because Aaron Judge didn't play. He had a .25 batting average, and then the second half of the season, he fell off to .231. So we see this pattern of dropping off in batting average after players participate in the home run derby. There's a theory behind this quote-unquote curse of the home run derby, that if you play in this competition where you're trying to only hit home runs, you could develop this really big uppercut swing to try and hit long balls out of the yard. And it messes up the mechanics of your swing. It makes it too uppercut, and you don't have as good of a swing for playing real baseball during the second half of the season. But most statisticians say there is no curse. It's a falsehood. It has nothing to do with their swing. There's no real curse. It's just the law of large numbers at work. It's just probability at work. You're thinking, what? How's it possible, given the data we've seen? Well, let's investigate. So here's what I'd like you to do. You're going to open the coin flip applet yourself that we used earlier. The link is in the description to it. You're going to set the probability of heads to 0.25, set the number of tosses to 100. Those parameters are right there. We're going to say 0.25 is the probability of getting a hit. So heads is a hit for a typical player, 0.25 batting average. And then 100 is the number of at-bats they're going to take in the first half of the season. So you're going to run the simulator, and you record the quote-unquote batting average from this. So I did this once myself, and you can see here that of the 100 tosses, there were 24 heads. So in this case, the batter batted 100 times. They got a hit 24 times. They had a .24 batting average. So they performed slightly lower than we would expect given their .25 probability of getting a hit. And then once we get to class, the 3 students with the best quote-unquote batting average will be our home run derby participants in class. Congratulations, you get to be in the home run derby. We're going to do a fake in-class derby, and then those same students are going to use the coin applet again with the same exact parameters as before, and we're going to simulate their second half of the season. Here's what I want you to think about before class. Do you believe these students will have a better or worse batting average in the second half of the season? Why? And what does this say about the home run derby curse? So please go ahead and do that simulation, see if you can get a really good batting average, and then think about this discussion question. That's it for today's statisticians. We'll see you in class.